And welcome to a series of clips based on chemical kinetics. In the first few clips we're going to look at more of the AS material in terms of Maxwell Boltzmann distributions and their effect on rates of reaction, and then in the later ones we'll look at more of the A2 material, whereby we will start to derive rate equations and discuss the Arrhenius constants as well. Prior to this, you will have studied GCSE Collision Theory and effects of concentration, pressure, temperature, etc. on rates of reaction, and I'll leave a link in the various descriptions to those GCSE discussions as well, because some of those principles that you learned there will still be relevant. So we will go straight into this discussion now, and what we have to now be aware of at AS is a new graphical interpretation of how we can look at the energy of a particle and look at the energies of particles in terms of the bulk processes and bulk properties of a substance. So we represent this in a graphical form, so called the Maxwell Boltzmann distribution, and it's a graph whereby we have energy on the x-axis and we simply have the number of particles on the y-axis, and we draw a curve which resembles something like this. So we have a curve whereby it starts at the origin, and this indicates that no particles have zero energy. So there is no molecules in a gaseous state that possess zero kinetic energy. And the curve then takes on a number of characteristic shapes. It goes up to a maximum point here, which demonstrates the most probable kinetic energy that a particle is likely to have in a sample. This is suggesting that if you have a bulk body of particles, then this is the most likely energy that you will experience of that number of particles. The curve then extends towards the right, whereby the energy of those particles decreases in probability. So the number of particles you are likely to find with very, very high energies will get very, very low. So this is high energies towards the right-hand side, and we've obviously got low energy towards the left-hand side of this diagram. And what this suggests then is that the higher in energy you go, the less likely it is to find a particle with that energy. Now, it's important to know as well that this axis and this curve will in theory never touch. It is statistically possible that you will always find one more molecule with slightly more energy than you just had. However, what is important to appreciate is that the area under the curve, i.e. all of the total area of everything, if you were to be able to integrate this, if you're a mathematician, this would tell you the complete total number of particles you have in that sample. That will become important when we start to change some of the variables, specifically temperature. When we look at temperature discussions, the area under the curve will quite often have to stay the same when you start to modify these diagrams. And so this distribution, as we say, is a very simplistic view of the number of particles within it. Now, what we also have is we are able to represent what will be the activation energy. So you've seen this type of discussion at GCSE before, where you had an energy profile whereby it was the peak that a particle had to get over before it was able to react. This energy, activation energy, is now a specific point on the x-axis, which indicates that only a small number of particles at any one moment in time actually have the desired activation energy. And this goes some way to explaining why in a chemical reaction most collisions don't actually lead to a reaction. Very few particles will actually lead to a successful reaction because they don't have the activation energy. The vast majority of particles don't have that activation energy. And so sometimes we then have to look at modifying how many particles have the activation energy, i.e. by increasing temperature, which we'll look at later, or by reducing the activation energy if we were to add a catalyst, for example. And that's why some of those GCSE discussions that I will link to are still relevant. You still need to be aware, even at AS, that the definition of a catalyst, something which can increase the rate of reaction without itself being used up, again by going via an alternative mechanistic pathway. So those definitions are still valid, but we've now got a slightly different demonstration of how the diagram looks, which is different perhaps to the type of GCSE diagram which you may have seen, which you will have seen, should I say, previously to your AS and A2 studies. So in the next few clips, what we'll do is we'll start to modify this Maxwell Boltzmann distribution, and we'll look at changing the concentration and pressure, but also changing the presence of a catalyst or by changing the temperature, and seeing how this Maxwell Boltzmann distribution can change and how we can then use that to explain how the rate of reaction changes based on and alongside GCSE ideas of collision theory, etc. So thank you very much, and I'll see you in the next clip.